Alright, so first of all, we're going to have a quick introduction of the graphs. So how do we define the graphs, or what are they all about? In simple words, the graphs, these are the pictorial representation of the data, and they help us to understand different quantities, the variation of one quantity with respect to another in a better way. We are able to visualize the information easily and in a faster way. So if you draw any graph, for example, I'm going to draw this one, then there are 4 pieces of information that you can get from any kind of graph. The first one is what you have on the x-axis. Alright, so I'm just adding a specific example in this one. I'm going to add time on the x-axis, and I'm going to add the velocity on the y-axis. Alright, so this is the situation that we have, and I'm going to remove the negative x-axis because our time cannot be really negative, and we have the negative y-axis because the velocity can be negative as well. Alright, so negative velocity, since velocity is a vector quantity, it can be negative, and negative velocity tells you or gives you the direction of the velocity. And the sign convention is, if the velocity is on the right side, it would be positive, and if you're moving on the left side, if your velocity is on the left side, the sign convention for the velocity would be negative unless mentioned otherwise. So this is a sign convention. Alright, so let's say you are provided with a graph that looks something like this. Alright, so let's get back to the same thing. We get 4 kind of informations, 4 pieces of information from any graph that you have. One from the x-axis, one from the y-axis, and one from the shape, in such a way that what is the gradient of that shape. So whether it be a curve, whether it be a straight line, if you find the gradient of that shape, that line, that curve, you'll be getting some information about the graph. And the last one is the area. Alright, what is the area of that graph? So what is the shaded area representing? Area under the line, area under the curve. So that would also give you some information. So let us apply these 4 properties in this graph, and let's find out what information can be obtained from this specific example. So x-axis tells you about the time, about the passage of time. Y-axis tells you about the velocity, like what is the velocity at any instant of time. Gradient, let's talk about the gradient. The gradient, you don't have to memorize it first of all. Like I've seen students, they try to memorize what would the gradient of a specific graph represent. If you're able to calculate it, then you can memorize. Well, let's try to find the gradient. So gradient is basically rise over run, y2 minus y1 over x2 minus x1. So the rise would be the change in velocity, because on y-axis we have velocity, so that would be change in velocity. What do we have on x-axis? It is time, so it would be delta t. Now what does this formula correspond to? Delta v over delta t, also described as rate of change of velocity. So if you recall your definitions, rate of change of velocity is called as acceleration. So in this specific case, the gradient of the graph would represent the acceleration. And at the end, we have the area. So for example, we have this graph, and in order to find the area, we have to find the area of this shape, which is the triangle. And the formula for area of triangle is 1 over 2 times base times height. So 1 over 2, it's a constant number. 1 over 2 constant number. But what is the base? The base is time. What is the height of this triangle? The height is representing velocity. So you try to recall your set of formulas, your set of definitions, and what is speed or velocity times time? It is displacement. So displacement equals to velocity times, or if it were speed time graph, then we could call it distance equals to speed into time. But in graphs, speed and velocity would generally mean the same thing, because the object, in most of the cases, the object is traveling in a straight line. If the object is traveling in a straight line, speed equals to velocity, and hence distance covered would equal the displacement. But then I remove this thing. Let's consider another example, and I say that now, let's say we're provided with distance, displacement here, or distance here. By the way, the symbols that we'll be using for displacement is either S or X. These are the symbols for displacement according to the new syllabus. And the symbol for distance is D. So D for distance, and S or X for displacement according to the new syllabus. This is the advised symbols for the Cambridge syllabus. But here you can assume distance equals to displacement because the object is traveling in a straight line. Alright, what would x-axis represent in this case? X-axis would give you the information about the time. Y-axis would give you the information about the distance covered. The gradient would be, in that special case, the gradient would be delta y over delta t, delta x, and delta y would be delta d over delta t, which is rate of change of distance covered, and that equals to speed. So that means gradient of this graph would give you the value of speed. Let's talk about the area, most important of them all. What do I get if I find the area of this graph? Instead of guessing it, let's try to find the area mathematically. So the formula is, for the triangle, the formula is 1 over 2 times base. The base in that case is time, and the height in that case is distance. So even if you ignore the constant number for a while, so here the formula for area would be distance into time. Okay, these two are being multiplied. Now, do you remember any quantity for which the formula is distance into time? And I'm sure that you won't remember any quantity for which the formula is distance into time, in which distance and time are being multiplied. Let's try to guess the quantity from the units. So what is the unit for distance? It is meters. And what is the unit for time? It is seconds. Now think about it. Do you remember any quantity for which the unit is meter second? I'm not saying meter per second. I'm saying meter second. So do you remember writing or studying any quantity for which the unit was meter second? And matter of fact, if you find the area of this graph, you'll be getting a number. It might be 10. Let's say the answer to the area was 10. But then what do you write with the unit? You'll have to write meters second. Now what is that quantity, which is distance times time, and the unit is meter second? It would be a meaningless quantity. Now that's why you'll recall this thing, that whenever they ask you to find the area of the graph, they used to ask you to find area of speed time or velocity time graph. And this is precisely why they never asked you to find the area of the distance time graph, because that would be a meaningless quantity. Now let me give you another example, a very important example. And they ask you the same question. They ask you to find the area, and let's say the shape of the graph is, in this case, let's try to draw a horizontal line. Okay? So this is the information that is given there in the question, and they ask you to find the area of the shape, and the question is, what does the shaded area of the graph represent? This shaded area. Okay, so, and the options are the options that are given there for this question. What does the shaded area of the graph represent? And this is the shaded area. So what we generally do is we just try to find the area irrespective of whatever we have. So it would be a rectangle, because we're not sure about if the length and width are equal. So it would be a rectangle. What do we have for the length? You can call it t. What do we have for the width? You can call it a. So let's say till here we have time t covered, till here we have acceleration a. So we get a quantity for which the formula is a into t. So directly we may not be able to come up with a formula or come up with a quantity for which the formula is this. So what we can do is we can break down the formula. So acceleration can be written as change in velocity over time, v minus u divided by t. Okay, and then this t cancels this one. What are you left with? You're left with v minus u, which is the change in velocity, or delta v. So in that case, the area of the graph will represent the change in velocity. So this is how we can find it. Sometimes the answer would be given, sometimes you have to work out the answer. And let's try to insert the units. So what is the unit of for time? It is seconds. What is the unit for acceleration? It is ms minus 2. So if we combine the units, meter would be there as it is. Then you combine these two using the laws of indices. This one is s raised to power 1. This one is s raised to power negative 2. According to the laws of indices, what do we get? Yes, s raised to power minus 1. So you see, unit wise, if we had gone through the units would not have helped us anyway, because for velocity the unit is meter per second, for the change in velocity the unit is meter per second, for average velocity the unit is meter per second, for speed the unit is meter per second. So in that special case, going with the method of finding the units and then finding the quantity would not have helped us, because all of the options have the same unit. There can be as many as 8 shapes for any graph. No matter what kind of graph you have, it would be made from these 8 shapes. Or sometimes it can be combination of 2 or more shapes, but if you break it down to the basics, there would be 8 shapes or 8 kind of shapes for any graph. I'm not talking about speed time, velocity time, distance time, displacement time. It can be any kind of graph. So those 8 shapes are divided into major categories. The first one is lines, and the second category is curves. Now how do you define a line, a straight line? Straight line has fixed gradient. This is how we define these ones, fixed gradient. And how many lines do we have? We have 4. And the curves are defined as variable gradient. If the gradient of the graph is different at different points, that means it is not a straight line, it is a curve. And how many curves do we have? We have 4. So let's talk about the 4 straight lines and 4 curves. 4 lines and we have 4 curves. So how many total shapes we would have? 8. And any graph in the world that would be composed of these 8 shapes. So what is the first one? The first one can be a line like this, which we call a straight line. The second one can be like this, which we call a horizontal line. A third line can be like this, a straight line can be like this, which is once again a straight line, but it has negative gradient because the line is sliding downward. It is getting away from the y-axis, positive y-axis. So it is having negative gradient. It is inclined line, but with the negative gradient. And then the last one is a vertical line. So in the graphs of kinematics, where we represent mostly we represent time on x-axis. So time here with the unit second. Okay, I'm not writing the unit, but the unit would be there, second. Now this shape may not be used because it would imply that the time remains constant and whatever you have on the y-axis is being increased. For example, distance or displacement, it is being increased even if the time stays still. So the last one may not be used. Let's talk about the other ones. So for this one, for the curves, we have one like this, the second one curve like this, the third one would be upside down like this, and the last one would be upside down but like this. So let's talk about the gradients. So if we have, let's talk about the lines. The gradient of the first one, the gradient is represented by m. So your gradient for this one would be constant and would be positive. Constant and positive. And matter of fact, I'm not writing the constant here because for the straight lines, the gradient is always constant. And matter of fact, this is how we define a straight line, a line with something with constant gradient. So let's talk about the second one. For this one, the gradient is 0 because the line is not steep at all. A horizontal line has 0 gradient. The gradient of the line, in simple words, is how steep a line is. So the steeper the line, the more the gradient. So for the third one, the gradient is constant, but it is negative. Why is it negative? Because the line is getting away from the positive x-axis, positive y-axis. It is getting away from that. So, or the line is upside down. The line is sliding downward. The gradient would be negative. And for the last one, the gradient would be infinite. Because for the gradient, you have the formula rise over run. So for the change in y, whatever the change in y is, let's say 6, 7, 8, whatsoever, but what is the change in x? Starting x was here, your ending x is here, so you get the change in x 0, or the run is 0. So 8 divided by 0, you hit it on the calculator, you get maths error, you get infinite. So this is something which we cannot calculate, so the gradient of this line would be infinite. Let's talk about the curves now. So curves do not have constant gradient, and if they ask you in paper to find the gradient of a curve, they would always ask you to find the gradient of a curve at a certain point, at a specific point, because otherwise the curves have different gradient at different points. So let's talk about the first one. The first and second curve, because they are getting away from the positive y-axis, towards the positive y-axis, or you can say more importantly, you can say the curves, these are rising, they are sliding upward, they're not upside down. So for these curves, the gradient would be positive. For both of them, the gradient would be positive. But at the same time, since the gradient is not constant, it is variable, and once it is variable, that leaves us with two options: is the gradient increasing or decreasing? For that fun, you have to check the gradient at two different points. You can check it at the starting point, and then you can check it at the end point. So let's check the gradient at these 2 points. How do we find the gradient of the curve? We find the gradient of the curve by drawing a tangent. So let me draw a tangent at the yellow shaded portion. It would be a line that looks something like this. And let me draw the tangent at the green shaded portion. The tangent would be something like this. Now, if I compare the steepness of these two tangents, I can safely say that this point would be having less gradient because it is more of a horizontal, but the next point would be having more gradient because it is more of a vertical. So what we say is gradually the gradient increases. So gradient is positive, but the gradient is increasing. Let's talk about the next one. For the next one, I'm going to choose two portions. I'm not going to draw the tangent, but you can assume that there would be a tangent on that. And if I check out the gradient at this portion, you'll see the line is more of a vertical, so it has high gradient over here. But at the next point, the line is more of a horizontal, so it has less gradient over here. So what we can say is the gradient is not constant and it is decreasing because line is getting more and more horizontal. Let's check out the next one. So first of all, for both of these, the gradient is negative because the lines are upside down, the lines are sliding downwards, so the gradient is negative. So I'm going to pick two portions. This is the starting point and this is the end point. So for the first one, you see at the yellow shaded portion, which is the initial part, the line is more of a vertical. Forget about upside down or downside up or the proper way up. The line is more of a vertical, so it has more gradient here, but at the ending portion the line is more of a horizontal, so it has less gradient over here. So what we say is the gradient in that case is negative and it is decreasing. So the gradient would be negative and decreasing, or decreasing negative, however you want to call that. For the last one, if you check out the initial portion, you'll see the line is more of a horizontal. At this portion, the line is more of a horizontal, so the gradient is less, and if it is purely horizontal, the gradient would be 0. And at the ending portion, the line becomes more of a vertical, so the gradient increases. So what we say for this one is the gradient is negative but increasing. All right, now the most important part. Whatever I have told you for the gradient, if we have all of these graphs, let's say 8 of these graphs we have, or you can, if you want to skip this one, you can, and we'll be left with 7 shapes. For all 7 shapes, if we have displacement here, in all 8 of them, I'm not talking about the first 4 or the second, in all 8 of them, we are drawing displacement time graphs. Okay, displacement time graphs. Everything that I've told you for the gradient would give you the information about the velocity. Every information that you have for the gradient is the information about the velocity. So let me choose any of the graph from here. So I'm going at random, I'm going to choose this one, for example. So for this one, like I said, all of these are displacement time graphs. So displacement on y-axis, time on x-axis. Then I ask you the question, tell me about the velocity of the vehicle for which the displacement time graph is shown. Which one? This one over here. So what do you say? Whatever the information was for the gradient, that is going to be the information for the velocity. So what you say is the gradient, the velocity is first of all negative, and then what you say is the velocity is not uniform because it's a curve and it has decreasing gradient, so the velocity is decreasing. So the velocity is negative and decreasing. And let me choose another one. For example, this one. What do you say about the velocity? The velocity is positive and decreasing. What do you say about this one? The gradient is 0, so you say it has no velocity. The velocity is 0. So that was the first part. In the second part, if all of these, now assume that all of these graphs are not displacement time graphs, rather these are velocity time graphs. Or in, like I said, if the object is traveling in a straight line, you can call it speed time graph as well. So let's say these are velocity time graphs. Sorry. So if these are velocity time graphs, VT graphs, and whatever information that you get from the gradient would be same information that you'll be having for acceleration, because the gradient of velocity time graph represents the acceleration. So let me pick up a random one, for example this one. So I ask you about the acceleration. What is the acceleration for which the velocity time graph is given like this? So you say first of all the acceleration is negative because the line is upside down. Then you say the acceleration is, since the acceleration is not constant, it is a curve, and the acceleration is increasing. So the acceleration is negative and the acceleration is increasing. So what is the negative acceleration? Since I have assigned you the video, I hope you go through the details, but in simple words, the negative acceleration is the acceleration towards the left side. The negative acceleration is just the consequence of the sign convention of the acceleration. So if the acceleration is towards the right side, it would be positive, and if the acceleration is towards the left side, it would be negative, no matter if you're speeding up or slowing down. And slowing down, no matter which direction you're slowing down, either you're slowing down towards the right side or either you're slowing down towards the left side, slowing down would correspond to deceleration. So this is all about the graph. They can replace it with some other thing as well. For example, I'm going to change these graphs from kinematics altogether, and I say that instead of speed time or velocity time, let me represent some other quantities here. So for example, I represent time on x-axis. In all of them, I represent time on x-axis, and on y-axis I'm going to represent change in momentum, delta p, with the unit of kg/ms minus 1 as the unit for change in momentum. So then I ask you the question, give me the information about the gradient and tell me what does the gradient represent in this case, in these graphs. What does the gradient represent? So what you do is you simply find the gradient by using the formula rise over run, or delta y over delta x. What is delta y? That is change in y, and on y-axis we have momentum. Let's write momentum over here. We have p on momentum on y-axis. So what would be the change in y-axis? It would be the change in momentum. And what would be the change in x-axis? It would be change in time. So what do you remember? Do you remember any quantity for which the formula is delta p over delta t, aka rate of change of momentum? Exactly, very good. So this is force. So every information that you get about the gradient is going to be the information about the force. For example, let me pick the last one once again. And on y-axis, I've represented the momentum with the unit of Newton second or kg/ms minus 1. X-axis we have time. Then I ask you, give me the information about the force. So what you say? You say, first of all, the force is going to be negative and the force is increasing. So not constant force, not 10 Newton of fixed magnitude, it keeps increasing. 10, 12, 14, 15, 18, 35, 120, it keeps increasing. So the force is increasing and the force is negative. Every information that you have about the gradient in this case gives you the information about the force, because force in this case corresponds to gradient.